By the summer of 1945, Britain stood victorious yet broken. The war had drained the treasury, shattered the industrial base, and left a nation that once commanded the largest empire in human history suddenly uncertain of its place in the New World Order. Yet in one domain, British supremacy remained unquestioned. The skies belonged to Britain. The Spitfire had become legend. The Mosquito had humiliated German defences. The Gloucester Meteor had ushered in the jet age, and in the minds of military planners, politicians, and engineers alike, maintaining this aerial dominance wasn't merely desirable, it was existential. The problem was that warfare itself had fundamentally changed. Hiroshima and Nagasaki had demonstrated that future conflicts would be decided not by massed bomber formations, but by single aircraft delivering unimaginable destruction. Britain understood this immediately. By 1947, the Air Ministry had begun developing requirements for what would become the V-bomber force. The Valiant, Victor, and Vulcan would carry Britain's nuclear deterrent throughout the 1950s, ensuring that despite economic decline and imperial retreat, Britain remained at the top table of global power. But military technology moves with terrifying speed. Even as the first V-bombers entered service, intelligence assessments painted a grim picture. Soviet surface-to-air missile technology was advancing rapidly. The SA-2 guideline system, first deployed in 1957, could reach altitudes that made high-level bombing suicidal. American U-2 pilot Gary Powers would prove this catastrophically over Sverdlovsk in 1960. But British planners didn't need that lesson. They had already seen the future. The solution seemed obvious. If aircraft couldn't survive at high altitude, they would have to attack at low level. But this created problems that nobody had ever solved. Flying at 500 knots, 50 feet above the ground, at night, in any weather, while navigating to a target hundreds of miles away and then delivering a nuclear weapon with pinpoint accuracy, this wasn't aviation, this was science fiction, and Britain was going to build an aircraft that could do it. The Royal Air Force needed this capability desperately. The English Electric Canberra, workhorse of bomber command and tactical strike squadrons across the world, was growing obsolete. First flown in 1949, the Canberra had been revolutionary in its day, but it lacked the speed, range, and sophisticated systems necessary for the nuclear battlefield of the 1960s. Replacement was not optional. What makes this moment in British aviation history so crucial is the sheer confidence with which planners approached the problem. Despite rationing still being a recent memory, despite the humiliation of Suez looming on the horizon, despite every indication that Britain was a declining power, the Air Ministry drafted requirements that would have made American engineers blanch. They wanted an aircraft that could penetrate the most heavily defended airspace on Earth, deliver tactical nuclear weapons with unprecedented precision, operate from damaged runways or even grass strips, and do all of this whilst carrying reconnaissance equipment capable of photographing Soviet tank formations from miles away. This wasn't merely ambition. This was a statement of intent. Britain would not accept second-tier status. Britain would not become dependent on American charity for its defense. Britain would build the most advanced combat aircraft the world had ever seen. The industrial capacity existed. The engineering talent existed. What nobody anticipated was that the greatest threat to this program wouldn't come from technical challenges or Soviet countermeasures. It would come from within, from politicians who saw military aviation as an expensive embarrassment. From Treasury officials who couldn't see past the next quarterly report, and from allies who had their own reasons for wanting British aerospace to fail. The stage was set for the greatest tragedy in British aviation history. The 1957 Defence White Paper landed on desks across Whitehall like a bomb, Defence Minister Duncan Sandys, son-in-law of Winston Churchill and a man who had himself been gravely wounded in the war, delivered a verdict that stunned the aviation industry. Manned military aircraft were finished. Missiles would handle everything. The future belonged to rockets and guided weapons, not pilots and airframes. At a stroke, dozens of promising projects faced cancellation. The Avro 730, a supersonic bomber of extraordinary ambition, was scrapped. The Saunders Roe SR-177, a rocket-powered interceptor that might have transformed air defense, was abandoned. Thousands of skilled workers received their notices. Design offices that had won the war found themselves empty. Yet the white paper contained a curious exception. Buried within its pages was acknowledgement that one category of manned aircraft would still be required. Strike and reconnaissance missions at low level, beneath enemy radar coverage, demanded capabilities that no missile could provide. A human pilot, making split-second decisions whilst skimming terrain at impossible speeds, remained irreplaceable. From this single caveat, the TSR-2 would emerge. The Air Ministry formalised its requirements in General Operational Requirement 339, issued in 1957. Reading this document today induces a kind of vertigo. The specification demanded sustained flight at Mach 2.05 at altitude. It demanded terrain-following flight at Mach 1.1 at 200 feet. It demanded a combat radius exceeding 1,000 nautical miles. It demanded the ability to operate from unprepared strips just 3,000 feet long. It demanded navigation accuracy sufficient to place a nuclear weapon within yards of its target after flying hundreds of miles at treetop height. And it demanded that all of this be packaged into an airframe that could be maintained in the field by ordinary ground crews. No aircraft in existence came close to meeting these requirements. No aircraft in development anywhere in the world was attempting anything similar. The Americans had nothing comparable. The Soviets had nothing comparable. GUR 339 was a document written by men who either understood perfectly what British engineering could achieve or had lost all contact with reality. History would prove it was the former. The contract to develop this impossible machine went to the British Aircraft Corporation, itself a newly formed entity created by government pressure to consolidate the fragmenting British aviation industry. BAC drew together the talents of English Electric, whose Canberra and Lightning had demonstrated genuine capability, and Vickers Armstrongs, whose expertise in large aircraft construction was unmatched. The partnership was uneasy from the start. English Electric's Warton facility and Vickers Weybridge works were separated not merely by geography, but by corporate culture and engineering philosophy. Yet from this friction came something remarkable. The design that emerged by 1959 represented a genuine leap forward in aviation technology. The aircraft would feature variable geometry engine intakes, allowing efficient operation from low-speed takeoff to supersonic dash. It would carry the most sophisticated navigation and attack system ever fitted to a combat aircraft. Its wing design, combining leading-edge droop with blown flaps, would enable approaches at speeds low enough for rough field operations while still permitting Mach 2 performance. The fuselage would be constructed using techniques borrowed from missile technology, with extensive use of steel and titanium in areas subject to aerodynamic heating. The engines would be Bristol Siddeley Olympus 22s, developments of the power plant that had proven itself in the Vulcan bomber. Each engine would produce over 30,000 pounds of thrust with reheat. The aircraft would weigh over 40 tons, fully loaded, yet would be capable of lifting off from runways that would challenge a light transport. Britain was about to build something extraordinary. The engineering challenges facing BAC's team at Weybridge and Warton would have defeated lesser organizations. Consider the fundamental problem of terrain following flight. An aircraft traveling at 600 knots covers approximately 1,000 feet every second. At 200 feet altitude, the pilot has roughly 0.2 of a second to react to any obstacle. Human reflexes simply cannot cope with this. The aircraft would need to fly itself, sensing terrain ahead and adjusting its flight path automatically, whilst the crew focused on navigation and weapons delivery. The solution was the forward-looking radar, designated the terrain-following element of the integrated navigation and attack system. This radar would scan the ground ahead, building a profile of the terrain and feed commands directly to the autopilot. The aircraft would rise and fall with the contours of the land, maintaining a preset clearance height regardless of what lay beneath. Nothing like this had ever been fitted to a production aircraft. The Americans were experimenting with similar concepts, but TSR-2's system was years ahead of anything flying in the United States. The navigation challenge proved equally formidable. Inertial navigation systems existed, but their accuracy degraded over time. After an hour of flight, accumulated errors might place the aircraft miles from its intended position. For a conventional bomber attacking a city-sized target, this mattered little. For TSR-2, tasked with destroying a specific bridge or command bunker, it was unacceptable. BAC's engineers developed a system combining inertial navigation with Doppler radar and a sideways-looking reconnaissance radar that could identify landmarks and correct accumulated errors. The pilot would program the target coordinates before takeoff, and the aircraft would find its own way there, day or night, in any weather. The sideways-looking radar itself was a marvel, capable of producing photographic quality images of terrain passing beneath the aircraft. It could identify individual vehicles from miles away, whilst the aircraft remained safely distant from enemy defences. Intelligence officers could examine the resulting imagery and identify Soviet tank battalions, supply dumps, or mobile missile launchers with unprecedented clarity. TSR-2 was not merely a bomber, it was a reconnaissance platform of extraordinary capability. Then there was the airframe itself, sustained. Mach 2 flight generates tremendous heat through air friction. The leading edges of wings and intake lips would reach temperatures exceeding 150 degrees centigrade. Conventional aluminium alloys lose strength at such temperatures. BAC's solution involved extensive use of titanium and specialized steel alloys in critical areas, combined with aluminium-lithium alloys where temperatures permitted. The manufacturing techniques required were so advanced that engineers had to invent new welding processes and develop novel approaches to machining these exotic materials. The wing design represented another breakthrough. TSR-2 needed to take off from short, rough strips, yet achieve supersonic speed at altitude. These requirements are fundamentally contradictory. Short takeoffs demand high lift at low speeds, which typically requires large wings. Supersonic flight demands small, thin wings to minimize drag. The solution was a relatively small delta-influenced wing combined with leading-edge droop and blown flaps. Engine bleed air would be ducted over the flap surfaces, energizing the boundary layer and dramatically increasing lift at low speeds. The wing could be made small enough for efficient supersonic flight, whilst still generating the lift necessary for rough field operations. The cockpit environment received equal attention. The crew of two, pilot and navigator, would sit in tandem beneath individual clamshell canopies. Their ejection seats, developed by Martin Baker, would be capable of saving their lives at any speed from ground level to maximum altitude. The navigator's station resembled something from science fiction, dominated by radar displays and the moving map that would show the aircraft's position relative to its programmed route. The morning of 27th September 1964 dawned grey and overcast at Boscombe Down, the Ministry of Aviation's test establishment on Salisbury Plain. Roland Beaumont, chief test pilot for BAC and one of the most experienced aviators in British history, had already flown Canberras, Lightnings and a dozen other types. Nothing had prepared him for what sat on the runway that morning. XR-219, the first TSR-2 prototype, represented the culmination of 7 years' work by thousands of engineers. Beaumont later recalled that despite his experience, his pulse quickened as he strapped in. The flight plan was conservative. Beaumont would take off, raise the undercarriage, make a gentle circuit of the airfield, and land. No heroics, no attempts to push the envelope. The aircraft was too valuable and too unknown for anything ambitious. Yet even this modest profile would reveal whether all those calculations and wind tunnel tests translated into reality. At 14 minutes past 3 in the afternoon, Beaumont opened the throttles. The twin Olympus engines roared and XR-219 began rolling. The acceleration was startling. Within seconds, Beaumont rotated and the aircraft lifted cleanly into the Wiltshire sky. The undercarriage retracted without incident. Beaumont flew a wide circuit, checking handling characteristics at various speeds, before lining up for approach. The landing was uneventful. The entire flight lasted just 15 minutes. But those 15 minutes changed everything. Initial assessments confirmed what BAC had promised. The aircraft handled beautifully. Beaumont reported that stability and control exceeded expectations. More flights followed in rapid succession. By October, XR-219 had reached 450 knots and demonstrated that the basic airframe was sound. By December, the aircraft had exceeded 500 knots. Then came the supersonic tests. On the 14th January 1965, Beaumont took XR-219 through the sound barrier for the first time. The transition was smooth, almost anticlimactic, but the data recorders told a remarkable story. Without reheat, cruising on dry power alone, the aircraft had reached Mach 1.1. This was extraordinary. Most supersonic aircraft required afterburner to exceed Mach 1. TSR-2 did it without breaking a sweat. Further test flights revealed even more impressive performance. During sustained supersonic runs, the aircraft demonstrated natural stability that astonished the test pilots. At Mach 1.5, handling actually improved compared to high subsonic speeds. Beaumont later stated that TSR-2 was the finest aircraft he had ever flown, and his logbook included types from Spitfires to the prototype Lightning. Jimmy Dell, the second test pilot to fly the aircraft, concurred entirely. The machine was exceptional. Word spread rapidly through the international aviation community. American observers who witnessed test flights returned to Washington with troubling reports. The British had built something genuinely revolutionary. Soviet intelligence, monitoring the program through various channels, reached similar conclusions. TSR-2 represented a capability that neither superpower possessed. If the aircraft entered service as planned, the Royal Air Force would operate the most advanced tactical strike platform on Earth. By February 1965, XR-219 had accumulated over 20 test flights. A second prototype, XR-220, was nearing completion at Weybridge. Production jigs were being assembled. The first operational aircraft was scheduled for delivery in 1968. Everything was proceeding according to plan. The technical risks that had seemed so daunting in 1957 had been overcome through brilliant engineering and relentless testing. Yet even as the test program accumulated success after success, forces were gathering that had nothing to do with aerodynamics or engine performance. In Westminster, men who had never seen TSR-2 fly were making decisions that would determine its fate. The aircraft's enemies weren't armed with missiles. They carried briefing papers and Treasury memoranda. Harold Wilson's Labour Party swept to power in October 1964, ending 13 years of Conservative government. The margin was razor thin, just 4 seats, but Wilson had ambitious plans for what he called the white heat of technological revolution. Paradoxically, this rhetoric of modernization would prove fatal for Britain's most advanced technological achievement. Wilson appointed Denis Healey as Secretary of State for Defence. Healey was intelligent, abrasive, and utterly convinced that TSR-2 represented exactly the kind of imperial overreach that was crippling Britain's economy. The financial arguments began immediately. TSR-2's costs had indeed risen substantially since the original estimates. What had been projected at around £90 million in 1959 had grown to figures exceeding £750 million by 1964. The Treasury seized upon these increases as evidence of catastrophic mismanagement. What they neglected to mention was that virtually every advanced military program in history had experienced similar growth. The American F-111, then under development, was experiencing cost escalation of comparable magnitude. Complex weapons systems simply cost more than initial estimates suggested, a reality that defense accountants have never fully accepted. Healey commissioned a series of reviews designed, critics would later argue, to produce predetermined conclusions. The aircraft's unit cost was calculated in ways that maximized the apparent expense. Development costs already spent were added to future production costs, inflating the per-aircraft figure dramatically. Alternative options were presented in the most favorable possible light, regardless of their actual readiness or capability. The general dynamics. F-111 emerged as the preferred replacement, despite the fact that it had not yet flown and was experiencing severe technical difficulties in American testing. The American dimension to this story remains controversial even today. Washington had its own reasons for wanting TSR-2 cancelled. American aircraft manufacturers faced no European competition if British aviation collapsed. American influence over NATO would increase if Britain became dependent on American equipment, and the Kennedy and Johnson administrations had made clear their desire for European allies to purchase American weapons as a way of offsetting the balance of payments costs of stationing troops in Europe. Whether active American pressure was applied to the Wilson government remains disputed. What is certain is that the F-111 purchase was presented to Cabinet as the obvious, sensible alternative almost from the moment Labour took office. Within the Ministry of Defence, a curious pattern emerged. Positive reports about TSR-2's test program received minimal circulation. Problems, real or invented, were amplified. When Beaumont and Dell reported exceptional handling characteristics, these assessments were buried. When minor technical issues arose, as they do with any prototype aircraft, they were presented as fundamental flaws. The narrative being constructed was clear. TSR-2 was an expensive failure that needed to be terminated immediately. The arguments extended beyond simple economics. Healey and his allies suggested that the aircraft was unnecessary for Britain's defence needs. Strategic nuclear deterrence was passing to the submarine-launched Polaris missile. NATO commitments in Germany could be met with less sophisticated aircraft. The reconnaissance role could be fulfilled by other means. Each of these arguments contained partial truths, wrapped in fundamental misunderstandings of what TSR-2 actually offered. What the anti-TSR-2 faction never adequately addressed was the industrial and strategic consequences of cancellation. Britain's aerospace industry employed hundreds of thousands of skilled workers. The design teams at Weybridge and Warton represented irreplaceable concentrations of expertise. The subcontractor network extended across the entire country. Cancelling TSR-2 would not simply terminate one aircraft program. It would inflict damage on British manufacturing capability that might never heal. But Healey had made his decision. Now he simply needed the excuse to implement it. The 6th of April 1965 should be remembered as one of the darkest days in British industrial history. Chancellor of the Exchequer, James Callaghan, rose in the House of Commons to deliver his budget speech. For the aviation industry, what followed was an execution disguised as accountancy. Midway through his address, almost casually, Callaghan announced that the TSR-2 program was cancelled with immediate effect. The chamber erupted. Conservative members shouted protests. Labour backbenchers, many of whom had constituencies dependent on aerospace employment, sat in stunned silence. The timing was deliberate. Budget speeches received parliamentary privilege. The decision could not be challenged or debated immediately. By the time proper scrutiny became possible, the deed would be irreversible. Callaghan offered the F-111 as consolation, promising that 50 of these American aircraft would be purchased to replace TSR-2. The cost savings, he claimed, would be substantial. Neither promise would prove accurate. At Weybridge and Warton, the news arrived like a physical blow. Engineers who had devoted years to the program learned of its termination through radio broadcasts. Production workers discovered that their jobs had vanished while standing at their stations. The chaos was immediate and total. But what came next defied rational explanation. Within hours of the announcement, instructions arrived at BAC facilities that went far beyond normal program termination. The aircraft were not to be preserved for potential future use. They were not to be transferred to museums in their current state. They were not to be made available for technical evaluation by allied nations. They were to be destroyed. The jigs and tooling that had cost tens of millions of pounds to develop were to be scrapped. The technical documentation was to be disposed of. It was as though someone wanted to ensure that TSR-2 could never be resurrected. At Boscombe Down, XR-219 had accumulated over 50 test flights and proven itself beyond any reasonable doubt. XR-220 had made its first flight just weeks earlier and was demonstrating equally impressive performance. At Weybridge, additional airframes in various stages of completion represented millions of man-hours of skilled labour. The order to destroy them seemed not merely wasteful, but actively malicious. Frederick Page, managing director of the BAC Preston Division and one of TSR-2's principal architects, fought desperately to save what he could. He argued that completed airframes should be preserved for posterity, that technical data should be archived, that the industrial capability should be maintained, even if the specific program was terminated. His protests were ignored. The orders came from the highest levels, and they were explicit. Nothing was to survive. The reasoning offered was almost insulting. Officials claimed that preserving the aircraft would create pressure for program resurrection, wasting further resources on false hope. Maintaining the tooling would impose storage costs. Keeping the documentation would serve no purpose since the aircraft would never enter production. Each justification was flimsy. Each ignored the obvious value of preserving Britain's most advanced aerospace achievement for future reference, training, or historical importance. Some within the industry suspected darker motives. Had assurances been given to American manufacturers that British competition would be permanently eliminated? Were their political interests served by ensuring that no future government could reverse the decision? Had someone decided that British aerospace independence itself must be terminated? These questions have never received satisfactory answers. What is certain is that the destruction orders were carried out with remarkable thoroughness. Within months, the evidence of Britain's greatest aviation achievement would be reduced to scrap metal and ashes. The few survivors would become museum pieces, stripped of their engines and systems, monuments to what might have been rather than functional examples of British engineering brilliance. The destruction began almost immediately and continued with methodical efficiency throughout 1965. At BAC's Weybridge facility, production jigs that had taken years to construct were cut apart with acetylene torches. These were not simple frames, but precision-engineered fixtures capable of holding airframe components to tolerances measured in thousandths of an inch. Replicating them would cost millions and require expertise that was being scattered to the winds as redundancy notices arrived daily. Workers who had built these tools now destroyed them, some with tears streaming down their faces. At Warton, the scene was equally devastating. Partially completed airframes were hauled outside and attacked with cutting equipment. Fuselage sections that had passed rigorous quality inspection were reduced to scrap. Wing assemblies incorporating thousands of individual components, each hand-fitted by skilled craftsmen, were torn apart. The aluminium and titanium would be sold for pennies per pound, a fraction of the cost that had been invested in transforming raw metal into flying machines. The technical documentation met a similar fate. Engineering drawings representing millions of hours of design work were gathered for disposal. Test data from Boscombe Down, the irreplaceable record of TSR-2's actual performance, was collected and destroyed. Computer tapes containing aerodynamic calculations and system specifications were erased or burned. The institutional knowledge that Britain had accumulated through 7 years of intensive development was systematically eliminated. Roland Beaumont witnessed some of this destruction and later described it as industrial vandalism on a national scale. He had flown aircraft throughout his career that were cancelled or superseded, but never had he seen anything like the deliberate erasure being inflicted on TSR-2. This was not program termination, this was cultural annihilation. Some materials did survive through the courage of individual engineers who defied orders. Drawings were hidden in private collections, photographs were smuggled out, technical reports were copied before the originals were destroyed. These acts of industrial, civil disobedience preserved fragments of TSR-2's legacy, but only fragments. The comprehensive documentation that would have allowed full understanding of what Britain had achieved was largely lost. Of the aircraft themselves, only 3 relatively complete airframes escaped destruction. XR-219, the first prototype with its 50-plus test flights, was eventually transferred to the Royal Air Force Museum at Cosford, but only after being stripped of its engines, avionics, and most systems of interest. XR-220 found its way to the Imperial War Museum at Duxford in similar condition. A third airframe, XR-222, which had been nearing completion at Weybridge, was preserved at Cosford as well. These survivors represent perhaps 10% of the airframes that existed in various stages of completion when cancellation struck. The human cost extended beyond immediate redundancies. Design teams that had worked together for years were dispersed. Engineers who had developed expertise found their skills suddenly unmarketable. Many emigrated, taking their knowledge to America, Canada, or Australia. The brain drain that followed TSR-2's cancellation weakened British aerospace for a generation. Young engineers who might have learned from these masters instead found themselves training in other industries or other countries. The subcontractor network suffered equally. Hundreds of firms across Britain had invested in capabilities specifically for TSR-2 production. Specialist machine tools, trained workforces, quality control systems all became worthless overnight. Some firms survived by diversifying, others simply closed. The geographic distribution of this damage meant that parliamentary constituencies throughout the Midlands and North felt the impact, though Labour somehow escaped electoral punishment. What replaced TSR-2 proved the final insult. The promised F111 purchase was itself cancelled in 1968, leaving the Royal Air Force with nothing. Britain had destroyed its own aircraft only to receive nothing in return. The cancellation of the American F111 purchase in January 1968 exposed the full magnitude of the TSR-2 disaster. Denis Healey, the man who had championed the American aircraft as the sensible alternative, now stood before Parliament announcing that cost escalation and technical problems made the F111 unaffordable. The aircraft that had supposedly offered such obvious advantages over TSR-2 would never wear Royal Air Force roundels. Britain had sacrificed its own world-leading program for precisely nothing. The Royal Air Force eventually received the Blackburn Buccaneer, an aircraft originally designed for the Royal Navy and never intended for the low-level overland strike mission. The Buccaneer was capable and served honourably, but it was not TSR-2. It lacked the speed, the sophisticated avionics, the terrain-following capability, and the reconnaissance systems that had made TSR-2 unique. Later still came the Panavia Tornado, a multinational compromise that entered service in 1982, 17 years after TSR-2's cancellation. The Tornado was effective, but its development had required sharing technology and design authority with Germany and Italy. Britain would never again attempt an advanced combat aircraft alone. Declassified documents from the 1990s revealed the extent of American involvement in TSR-2's fate. State Department cables showed that Washington had actively encouraged cancellation, viewing British aerospace independence as an obstacle to American commercial and strategic interests. Pentagon officials had privately disparaged TSR-2's capabilities whilst simultaneously expressing alarm at its genuine advances. The hypocrisy was breathtaking. American manufacturers secured contracts that might otherwise have gone to British firms. American influence over European defence procurement increased substantially. The special relationship, it seemed, flowed primarily in one direction. The financial arguments used to justify cancellation proved equally hollow when examined with hindsight. The supposed savings evaporated as replacement programs consumed equivalent resources without delivering equivalent capability. The balance of payments, costs of purchasing American equipment exceeded what domestic production would have required. The unemployment resulting from aerospace redundancies imposed welfare costs that offset Treasury savings. Economists who studied the decision concluded that cancellation made no financial sense even by the narrow criteria that had supposedly demanded it. The strategic consequences extended for decades. Without an indigenous advanced combat aircraft program, Britain lost the ability to develop certain categories of military technology independently. Design teams that might have produced successors to TSR-2 instead worked on components for American or European programs. The supply chain that had supported independent British aerospace fragmented irreparably. When the time came to replace Tornado, Britain found itself dependent on international partnerships that diluted national control and exported jobs. Those who visit Cosford or Duxford today can still see the surviving TSR-2 airframes. They sit in their museum halls, stripped of engines and systems, monuments to political cowardice and institutional sabotage. The aircraft that Roland Beaumont called the finest he ever flew will never take to the skies again. The technology that terrified Washington and Moscow alike has been reduced to static exhibits for school children to photograph. The men who built TSR-2 are largely gone now. Frederick Page died in 1905. Roland Beaumont passed in 2001. The engineers and craftsmen who translated impossible specifications into flying reality have retired or departed. Their achievement deserves to be remembered not merely as aviation history, but as a warning. Nations that destroy their own capabilities in pursuit of short-term savings discover eventually that some things, once lost, cannot be recovered. Britain built the most advanced combat aircraft of its era, then Britain deliberately destroyed it. The reasons offered were financial, strategic, political. The truth was simpler and sadder. Britain lost faith in itself. That loss of faith cost far more than any aircraft program ever could.